MJ15, P42, question 7. A solenoid is connected in series with a resistor. Ooh, we have a resistor now. Usually it's a voltmeter. And you have a magnet approaching, and this is how the magnet is moving. As the magnet is being moved into the solenoid, thermal energy is transferred in the resistor. Use the laws of electromagnetic induction to explain the origin of this thermal energy. Where the energy come from? The resistor actually will get hot. So will the coils, but the resistor will be the main one dissipating energy. Why suddenly got energy? Come out from nowhere? Gotta come from somewhere. So we have seen this set up many times. It's our favorite good old moving stuff into the field. So the magnet has some kind of magnetic field. As you move the magnet towards, there's a change in flux. You can say the coil is cutting the flux, or the magnetic field strength inside this coil. Magnetic flux density is changing because see, the lines are much closer. So B is increasing as you move in. So if you keep changing, keep causing some flux, you see the light bulb will light up, right? That's some light energy dissipated. But what if you replace this with a resistor? Then you got some thermal energy only dissipated, no light. So how do we explain this phenomenon using our 4 good old steps that we talked about in the theory video? Step 1, ask yourself, what the flux is happening? Who's changing the flux? What is the flux changing? Where? In what? Who's causing the change? Number 2, ask yourself, Faraday's law. If there's a changing flux, there is a induced e.m.f, and you're going to talk about that. So I'm going to pause here. Who's causing the change in flux? In the beginning, there is no flux in the coil or the solenoid. Then as you bring the magnet closer, suddenly there is a flux in the coil. Because, well, some flux. Because this magnet has its own magnetic field. I'm not going to draw the whole thing, but it generally looks like that. And it actually goes for forever. It's actually a very long one, like this. But we don't draw so much because the diagrams will get real messy. So you have this flux that is increasing. Okay, before that you can say it's 0. But after a while, when you bring the magnet closer, the flux is increasing. Why is there a flux increasing? Because B is changing. I mean, the cross-section area should still be the same, so the area is not changing. B is changing. So yes, we've identified the change in flux. Should we write about that? Wait, let's plan first. So we know, yes, there's a change in flux in the coil because of magnet. Number 2, so there's a change in flux, there will be an induced EMF. Potential difference. I guess you could measure potential difference kind of here. PD, which is the EMF. And then number 3, you could talk about Lenz's law, just in case if you're not sure Lenz's law will get you a mark or not. So Lenz oppose the change. Current will be generated to oppose the change. The field. So Lenz's law, a current will appear to generate a field to oppose a change. And lastly, if needed, let's talk about energy. And I think this is a really important part because they want you to answer the question, where did thermal energy come from? So we have to talk about energy conversion. What energy is changing? Where did energy come from? Okay, so with this in mind, let's proceed to write it out. Number 1, flux. Where is the change in flux? Let's talk about that. So I'm going to start off by saying, as the magnet approaches the solenoid. So the magnet comes closer with some velocity. I guess it approaches solenoid. There is a change in flux. So we're going to say that there is a change in flux. And this flux inside the coil. So I add that in coil. Okay. So what happens to this flux? This flux will cause what we call an induced EMF. So I'm going to say change in flux. What should I say? This change in flux, I'm going to shortcut and just say change in phi causes or induces an EMF or current in the coil. So here's number 1, number 2. But since we're here, let's talk about Lenz's law as well. This current will be generated in such a way to oppose the change. So we look at the diagram hor. At first, there's not much. Suddenly, there's a very strong B that is pointing to the left. The coil does not like change. So it's like, ugh, oppose the change, oppose. Why is there so much arrow pointing to the left now? Oppose, oppose. So it creates its own magnetic field that opposes this change. So something like that. So that means this electromagnet now has a north and a south. So north repel north. So it does not want the magnet to come in. It says, no, 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 oppose. So where will the current be flowing? You're going to take your right hand grip rule and then you do your curl. That's where your fingers will be curling. So that will be pointing down. So I'm going to draw a few arrows to show the direction of current. So that means up and down and into here. Oh, so we have a current flowing now. Yes, it's a complete loop. Now you can have current flowing and you will dissipate energy. So we're going to talk about that. All right. So the changing flux induce an EMF or current in the coil. I finished writing. Current in the coil that opposes. So we're going to talk about the Lenz's law. So current in the coil that, let me move this up so my head doesn't block it. Generates a field of flux that opposes the magnet's motion. So purposely one lah, they don't like change. So change the magnet's motion. Okay, I think I'm pretty satisfied. We got Faraday, we got Lenz, opposed motion. Okay, what next? We haven't answered the question, why is there thermal energy, right? So when there's current, you can have energy loss. How do we calculate energy again? Oh, right. E equals to VIT from AS, energy dissipated in a resistor. So if you have PD, you got current, over time, you will dissipate energy. Oh, right. But don't need to talk about equation. We're going to talk about energy. So next, we are going to say that because of this opposition, you will need some energy to give the magnet so that it can push through. Because it's opposition. They're going to repel. It's a repulsive force. So you have to hold the magnet and force it to go in. So that's energy done by you. Kind of work done by you to push the magnet into the coil. So we're going to talk about that. So, energy needed is needed to move the magnet into the coil. So there's like work done. Into the coil pula. Into the solenoid. That's a better word. Solenoid. Let's call the things by their names. So this is what we recognize as work done. You are doing work to move the coil in. Otherwise, the magnet won't even go in. It just like opposite repulsive force and then just stuck there. It will not go in naturally by itself. So you have to push it in with some force, some external force. Okay, well, what do we have to answer? So we talk about energy is needed. The energy from you pushing the magnet in is converted into electrical energy and converted into heat energy. So electrical energy is the E equals to VIT, but also heat. Thermal energy. So the conversion goes from mechanical, electrical, to heat dissipated by the resistor. Oh, so let's write the last part. Almost there, almost there. So this induced current causes a resistor to dissipate heat. Induced current can already mean electrical energy lah. So if you want to just summarize what's the energy changes, you got some kind of mechanical energy from your hand doing work converted into electrical energy, so induced EMF, so a current, and that current when flow through a resistor become heat, so thermal energy. That's the conversion happening here lah. Wow, this is a long essay. 4 marks, where do they come from? Number 1, induced EMF currents because of a changing flux. Did I mention that somewhere? Here, induce an EMF. So this is B1. They didn't give mark for change in flux. Never mind. Sometimes they give, sometimes they don't give. You just write to be sure. Number 2, if you talk about current generated a field that opposes the magnet, that is, where is it? Here, a field that opposes the magnet. So this current will oppose the magnet. That's Lenz's law. So you refer to Lenz's law. That's another mark. Then you talk about, oh, actually you need energy to push in. Oh, okay. So energy is needed to move. So you talk about the idea of work done. That's this one here. Lastly, you talk about energy conversion. So you did work to push the magnet. It became electrical. Electrical became heat. So this is the last part. Resistor dissipate heat. There we go. Wow, it's a long story. Do we have to explain some more? Oh my goodness, this is the explanation question. 4 marks one essay, 4 marks another essay. Hang in there. Now we are looking at an alternating current in the transformer. Oh, but they're asking an interesting question. Explain, give reasons, why the AC in a transformer is not in phase with the EMF in the secondary coil. So if you remember the graph we drew in the theory video just now, in the previous video, then you will know why. But in case you don't remember, here's the reason why. In a transformer, you have one coil, and a secondary coil. So in the primary coil, you will have an alternating current going back and forth. So this is current. Current will generate a field. Wait, wrong direction. Yeah, never mind lah, okay. Current generating a field moving in certain direction. And this field or flux links together both coils. Now, if we draw the graph of the first one, it looks like a sine, can be either sine or cosine. Okay, so the current in the primary coil looks something like this. Could look something like this. But how does the EMF look like in the secondary coil? So EMF will be measured over here with a voltmeter. You need to remember, how does EMF induce equation work? So EMF induced in the secondary coil, I'm just going to call this coil Q. So this is P, coil Q. This is related to the rate of change of flux, but also negative. How do you find flux? Flux is related to the current in P. How do you know that? Well, flux, firstly, through, let's say, P, is B times A. But B is related to I. Hence, you can say that, oh, since B is related to I, so I can conclude that the flux through P is proportional to the current through P. So this graph really can be current, or the field through P, or it could be the flux through P, and you will see the same oscillating shape appearing there. So now you need to know gradient. When you see d phi dt, d something dt, rate of change, that is gradient now. So you need to find the gradient. Okay, let's find the gradient. So gradient here is 0. Okay, so I'm going to put a 0 point there. Where else? Gradient here, also 0. So I'm going to put a 0 point there. Where is the biggest gradient? This one looks pretty big, positive gradient, but because of the negative sign, positive gradient, I'm going to put a negative number down here. Where else? Here got negative gradient, so I'm going to put a positive EMF induced. Last part, positive gradient, means a negative induced EMF. So something like this. So if I connect all the dots, I should get what we call a cosine wave like this. What's the phase difference between both? If I pick a reference point, such as maybe this point, reference point is here, there is a phase difference here, about 90 degrees. Is that always true? Yeah, when you see like a d phi dt thing, I got like 90 phase difference. You differentiate sine, become cos. So if this is a sine graph, you differentiate, it becomes negative cos, which is this one. Negative cos. This will be a sine graph. And there's always all the 90-degree phase difference between all these sign, cosine, negative sign, positive sign. So yeah, that's why a phase difference. So how to explain this? Phase difference because of Faraday's law. So how do we do this? Okay, let's go and see the answer. Explain. Number one, let's go through the steps. Change in flux. We'll always start with that. So is there a change in flux? Yes, there is. Why is there a change in flux? Because the current in the primary coil, I'm just going to use the names because P and Q is created by me. Primary coil causes a flux or a magnetic field. So because there's current, there's a field. Also it's alternating, but hang on a second, we'll talk about that. So you have a current in a primary coil and the flux in the core of the transformer is in phase with the current, with primary current. Okay, let's put it that way. Primary current. So what am I referring to? In a transformer, you have two coils, ma. I forgot to put the iron core for you. Okay, here's the iron core. Let's draw it. Iron core is going to look something like this. There we go. We have linked both together. So when you talk about in phase, this in phase is referring to this current and the field that it generated. I mean, got current, got field. In phase also, you must mention that since they're asking about phase. So we want to specifically mention the phase on how these two relate. Okay, so we talk about that in phase primary current. How does that relate to the secondary coil again? So far, we only talk about primary current. What about secondary? So here's where we go to that. So, how is the secondary related? They are linked. See this iron core down here? The magnetic flux linkage links both coils together. So we're going to talk about the linkage. So this magnetic flux links the secondary coil to the primary coil. I'm just going to write links the secondary coil. Okay, and it's changing, right? Because if your current in the primary is alternating, means your flux is also changing back and forth, forward, backward, forward, backward. So up, down, up, down. So there's a change in flux. So we are going to mention that. So, and this change in flux, I'm going to shortcut and just write delta phi, induces EMF. We talk about Faraday's law. Induces an EMF where? In the secondary coil. Now it's very important. You bring the secondary coil into the picture. But we haven't talked about the phase yet, right? Oh, rate of change, Faraday's law. Oh, right, we haven't mentioned the equation yet. So, we name dropped Faraday's law. How do we know induced EMF? Let's just continue the sentence then. Induced EMF in secondary coil, which is proportional to the rate of change, the d phi dt, rate of change of flux. And when you have a d phi dt of some kind of alternating curve, will be out of phase already, not in phase anymore. Hence, final sentence, induced EMF is not in phase with the primary current. Primary alternating current, no more space there. So alternating current generates the flux. The flux induces EMF, and the EMF is not in phase with the flux. Because you're looking at the rate of change. So think of gradient lah. Wow, 4 marks for this. Where do they come from? Number 1. First one comes if you talk about where the flux comes from. Current causes a flux. Okay. Can. That's the first part. But how does that flux relate to the current? In phase. Okay. B1. Because got current, got flux. Okay. Then we talk about the secondary coil. So the first part you talk about explain the primary coil, then you explain the secondary coil. Secondary coil, if you talk about the magnetic flux linking both coils together, that is this one right here. No space to write, so I'll just write here at the side. That's important because it is saying that your primary flux and the secondary coil, secondary flux is the same because they are linked together. Okay. And when there's a change in flux, what happens? We talk about the rate of change. So induced EMF is the rate of change. So this whole part, induced EMF, rate of change of flux. Faraday's law. And kind of from there, they assume that you already know that if it's rate of change, there will be a 90 degrees phase difference. So not in phase anymore lah. Cannot have the same phase. Not in phase. In phase means one is like this, the other one also like that. In phase, there's no phase shift or phase difference between both. Whew, okay, so that is how you can explain transformers phase relationship between induced EMF and the current that generated the flux change. Okay, it may be good to summarize this in somewhere in your notes because it's a pretty important one. 4 marks and 4 marks. Wow, lots of essays. This whole chapter is just essays everywhere. Look at all this. Alright, so that's all for this video. Hopefully that helped your understanding. Go check out the next few ones that we're going to be posted to better understand different scenarios of mutual inductance between two coils. But that is all for this video. I will see you in the next one.